So the next algorithm is naive Bayes or naive Bayes. Again, it is depends on your convenience with respect to the pronunciation. So I'll go with naive Bayes. So naive Bayes is algorithm is a supervised learning again, which is based on Bayes theorems. Okay, which is usually for solving classification problems. So uh, it's a theorem and assumes that the predictors are independent. So in other words, the classifier assumes that the presence of a particular feature in the class doesn't affect the presence of another one. So it is independent of features. So again, features, parameters, uh, columns. Okay, so it is mainly text classification that includes high dimensional training data set. So high dimension, when I say high dimension, so basically we do consider higher dimension. So again, uh, with an example which would make clear later on in this video. So again, it is a probabilistic classifier, which means it predicts on the basis of probability of an object. Some of the popular examples for naive Bayes would be something like spam filtration, in sentimental analysis, and also classifying uh, articles. Okay, so again, it is there is a reason why it is the name is known as a naive Bayes. So the name of the classification technique is naive is because the reason that the model assumes the feature are conditionally independent. So basically assumes the occurrence of a certain feature is independent of the occurrence of the other features. So such as if a fruit is identified based on color, shape and taste, so then a red spear and a sweet fruit is recognized as an apple. Okay, so it is irrelevant. So hence each feature individually contributes to the identity that it is an apple without being dependent on each other. Okay, so probably here we might get few silly mistakes such a way that like if you're going with some kind of orange color with a again shape of round and with respect to sweet, then you will definitely go with sweet or kind of sweet and sour, which you will go with the orange rather than going with an apple. So you cannot assume like yellowish orange something like that. So it will based on like again based on all the number of outcomes, so it will predict one of them. Okay, so again it is called as Bayes because of Bayes theorem. Okay, so basically I'm telling this Bayes theorem. So what exactly is this Bayes theorem? Okay, so we'll see with an example. So if A and B are two events, then the formula for the Bayes theorem is given by conditional. We'll just recall the conditional probability. So that is probability of A by B is equal to probability of A intersection B divided by probability of B. So the Bayes formula is this one. So basically the theorem is which is used to determine the probability of hypothesis with prior knowledge. Okay, so it depends on the conditional probability. So here probability of A by B where we are seeing in conditional probability is posterior probability. So that means the probability of hypothesis A on the observed event B, and probability of B by A is the like likelihood probability. So probability of the evidence given by the probability of hypothesis is true. So this is why we use the Bayes formula. So again the Bayes formula tells that probability of A by B B by A is equal to probability of A by B multiplied with probability of B and divided by A. Okay, so just substituting back the conditional probability over here, probability of A by B uh, that is equal to a probability of A intersection B divided by probability of B. So over here what happens is the multiplication of probability of B and division of probability of B would cancel out, and finally we'll end up with a formula as probability of B by A is nothing but equal to probability of probability of A intersection B divided by probability of A. Okay, so here again probability of A can be is known as usually prior probability. Okay, so this is the probability of hypothesis before observing the evidence, and probability of B is marginal probability, that is the probability of evidence. Okay, so that is with respect to Bayes theorem, and applying Bayes theorem to understand conditional independence. Okay, so we'll have We'll see with an example again. So we have a question like let event A signify the occurrence of a head and event B excuse me. So event B be the occurrence of 1 on a dice of roll. So basically we are when it comes to head, so obviously it is tossing a fair coin, unbiased coin, and event B is nothing but getting 1 on the dice, so rolling a unbiased die. Okay, so find the probability of given that occurs that A occurs. Okay, so probability of B when A occurs. Okay, so that is the probability question. So what is the probability of A? We already know it is 1 divided by 2. So the occurrence of or the probability of heads occurring is 1 divided by 2. Again, just go back and revise with respect to probability, you will understand. And probability of B is 1 divided by 6 out of 6 conditional, only 1. Okay, so what is intersection of this? So it is independent of each other, right? So we had seen an example also when it comes to Venn diagram. Okay, so probability of A intersection B is a multiplication of them. So as there is no intersection point, so it is directly multiplication, like probability of A into probability of B minus probability of A intersection B. Okay, so that is like minus 2 into A intersection B. So as there is no intersection points, so we'll be having our probability of B by A. So again here we have not calculated, but it is 1 divided by 2 into 1 by 6 is 1 by 12. So probability of B by A, just substituting back the base formula which we saw in the earlier slide. So probability of B by A is probability of A intersection B divided by probability of A. So probability of B by A is nothing but 1 divided by 12 whole divided by 1 by 2. Okay, so just work around with simple maths over here. So the 1 divided by 2, the 2 denominator will come back in the numerator and 2 will get cancelled out with 12 6 times. So hence we'll be getting the final probability of 1 by 6. Okay, so again here the probability of B by A is same as probability of B. Okay, so there are as they are conditional independent. See, irrespective of probability of B with the event of occurring of A, so it is still 1 by 6. The probability has not changed. So this is what naive bias is, naive Bayes or naive bias. Bayes it is naive Bayes or naive Bayes. Okay, so that is the condition. Like with an example, I hope everyone has understood. Now a bit more information about naive Bayes. So basically here we can like generally the example which we saw was having only one conditional statement. But usually it is like the event will have multiple features. Okay, so here probability of y divided by x1 comma x2. Okay, so at this scenario what happens is the base formula is nothing but probability of x1 by y into probability of x2 by y into probability of y. Okay, a whole divided by probability of x1 into probability of x2. So this is for 2 features. So this is for 2 features. So usually it might be even more than 2 features. So again we'll see that we'll see with respect to an example. So as I was telling here we'll consider our x1 as a good and x2 as a bad, so positive or negative or something like that. So this is the conditions. Okay, so now the probability of y on good comma bad will be equal to probability of good by y, probability of bad by y into probability of y divided by probability of good into probability of bad. So we'll see a table over here. So basically x1 will consider as marks, x2 will consider as curriculum. Okay, so here marks would be like this is we are checking whether there is a probability of getting admission or not. Okay, so this is the usually the training case. Okay, so when marks is good and extracurricular is bad, still it's okay, you will be getting the admission. When marks and extracurricular both are bad, sorry to say that you are not going to be getting any admission. So the admission status over here is N. N means no, Y means S. Okay, and finally marks marks is bad but still extracurricular is good. So maybe they will try out something with respect to your sports quota or something. So that's why your admission again status is good. Okay, so now let us calculate the possibilities, and also here with respect to good and bad. So this good is for x1. Okay, so you need to check with respect to here x1, right? So x1 good, what you need to check, bad is the the negative impact. Okay, and here probability of x2 being bad means we are taking the probability of bad over here, okay, in the extracurriculars. So remember this good is belongs to x1, which is marks, and this bad belongs to this one, and same goes for this denominator also. Okay. Here we have a table. So basically, just clarifying with respect to the previous this one. So for x1, the number of goods what we saw, and the probability of getting yes is 1. Okay, so it's just if you just go back and check the table. So here with respect to x, so we have one good and the problem, and it is yes. Okay, it is not no. So the admission status is yes. So that is what we have specified over here. And with respect to good and getting a no is all was 0. And with respect to bad, there was two conditions. Like we had two bads. Okay. So basically, it occurred in both yes and no situations. So if you just go back and check with respect to the table, we have two bads with respect to marks. So again, it was dependent on the extracurriculars, but still here it is like independent. So bad, we have n and we have s. So both conditions arise. So that's why we have 1 and 1. So what is the total? So 2s and 2 and 1 no. Now let us calculate the probability of x1 over y. Okay, so it is obviously you can understand here it is directly like 1.1 by 2. Okay, so again go back and refresh probability to understand this. And with respect to bad also, it is 1 over 2. So it is like the half of the chances that you will be getting with respect to having marks. Okay, so this is because it depends on your extracurricular also. And what about the probability? Okay, so the probability of getting no, whereas this one is actually 0 out. Okay, so if you are good at x1, so basically marks, you will definitely get a probability. So that is like rejection is not there. Okay, acceptance is like half of it, but rejection is not there. So that's why the no of x1, the probability of x1 over n is 0. And whereas when you are bad at marks, again the rejection is quite higher. Okay, and again just calculating the total probability. The total probability should always be unity, right? So it should be 1. So that is like calculating probability of all the conditions. You will be ultimately getting the value as 1. So that means 100%. Okay. So again, I will just leave this to you guys to fill out this table. So you can just pause the video and solve it, or take a screenshot, solve it later. Okay, so I have just leave blank, and ultimately, obviously, the total of probability is 1. So that is why I have already written once over here. So now going back to with respect to the problem. So here good and bad is y, bad and bad is no, bad and good is y, which we had already solved. So going back with respect to the we just calculated the probabilities, right? So probability of good over y would be nothing but half, and probability of bad over y is nothing but half, and probability of y is 2 out of 3. Again, whole divided by good into bad. So that is nothing but 1 divided by 3. Again, this 2 by 3, 1 by 3 values are obtained by the x2. So like if you solve this, if you solve the table which was blank, you will get the values. So ultimately, this is the probability of y over good comma bad. So and then the chances of getting in. Okay, so the chances of getting in or getting an admission is over 75%. Okay, so that is about naive bias. So in the next video, we'll be seeing about SVMs.